All right, we've got a maximum minima problem here. This is the case where we've got a minima, and this is question 5 from an HSC exam, 2009 or 2010, I think. Normally not as difficult as you would see a max-min problem in an HSC. Normally they feature in about a question 9 or 10 of the old papers, or sort of a 15 or 16 in the new style of papers with multiple choice. But it's the exact same premise and similar number of marks here. It's just not quite as hard, which is a good thing to have a look at. So really, if you're getting daunted by tough max-min problems, try this one and see whether you can't work out the sort of structure that we follow and the steps that we take, because really all that gets harder is setting up the equations and then the algebraic skills involved in doing that and differentiating. Okay, so we've got a rainwater tank is to be designed in the shape of a cylinder with radius r and height h, both in meters. Now the volume is to be 10 cubic meters. Let A be the surface area of the tank, including its top and base in square meters. Okay, deciphering that. We know our step 1, straight away, step 1 is going to be 2 equations. Okay, I'm going to need 2 equations straight away. The good thing here is that we are given 1. Okay, now I'm trying to minimize A. So that means I will be differentiating with respect to A, and this is actually going to be the basis for what I'm differentiating here. This equation, sorry about that, right here. Now the other thing that I'm given here is the volume is 10. Well, the volume of a cylinder is very easy. That's our volume equals pi r squared times h. Okay, surface area of the base times perpendicular height. That's the basis for any prism, of which this is a circular prism or a cylinder. Now we also know that's equal to 10. Okay, so that means pi r squared h equals 10. Well, the thing my issue here is this h. So the way we get around that, and what we've got our 2 equations for, is that if I can now generate an equation here, h equals 10 on pi r squared, by making h the subject, essentially what I've got is my 2 equations. Obviously we said we've got number 1 here, and then number 2's down here. So I'm going to put that second expression into the first one. Okay, so my area will therefore be 2 pi r squared. That doesn't change. Pi is a constant, and then I've got 2 pi r times my new expression for h, which is 10 on pi r squared. Just looking at that, by the way, how am I going to get something here that's got 20 on r? Well, I could get it by going 2 times 10. The pi's will end up cancelling each other out. That's just a little clue that's going on in my mind as I think about how am I going to generate this equation here, this single equation with just one variable in it. Neaten that up. Again, the first part doesn't change. 2 pi r squared plus, well, it's 2 times 10 is 20. R divided by r squared, or r on top, and r squared in the denominator ends up with just r in the denominator, and of course, as I said before, the pi's cancel each other out. Okay, we've shown that. We've shown all our steps. Okay, I'll put a little note there, don't skip steps. Okay, if you'd really like to show some sophistication, I'd suggest putting this in brackets here as I've done. That just shows that is your h. Okay, you have literally replaced or substituted using the 2 simultaneous equations. You've replaced h with 10 on pi r squared as you've generated down here. And again, don't skimp on how you actually found that. Go through and write these steps here. Go write them out. Go write out every single one and end up with your 2 equations. You don't have to name them 1 and 2, but that's how we show you're given that equation. So even if you couldn't do it, you could still go and do part 2. So to actually earn these 2 marks here, you do have to be very clear in how you've shown those steps. Okay, so now that we've shown this, we've shown that A being surface area equals 2 pi r squared plus, I'm going to rewrite that as 20r to the negative 1 because I know I'm going to be differentiating it. Show that A has a minimum value and find the value of r for which the minimum occurs. Okay, I'm going to go dA on dr. Remember, I'm minimizing A, so it's dA over dr because I'm going to find a value for r which gives me a minimum area. is 4 pi minus 20 r to the negative 2. That's just our standard differentiation technique. Again, I'm treating pi like a constant there. I'm not differentiating with respect to pi. And actually, I've forgotten that should be 4 pi r, not just 4 pi. So what I end up with is 4 pi r minus 20 on r squared. I'm going to go make this one fraction. You'll see why. I end up with 4 pi r cubed minus 20 on r squared. Okay, good. We've differentiated. Now the reason I've gone and made it into a single fraction is because it will make it easier to solve. Now straight away I'd look at it and say, well, r can't be 0. Mathematically r can't be 0 because I can't divide by 0. Practically r can't be 0 because if I let r equal 0 in there, I don't have a cylinder. Okay, I don't have a shape, I have a flat line, and that just makes absolutely no sense. So straight away I know r can't be 0. It's not going to be an issue for us, but what we'll end up doing is we're going to go and show that dA on dr equals 0. We also need to prove that it has a minimum. That's actually the first part of the question, show that A has a minimum value. So I'm going to go let this equal 0. Well, we've already decided the denominator can't be 0, but the numerator can equal 0, so that will mean that 4 pi r cubed minus 20 equals 0, or 4 pi r cubed equals 20. Pi r cubed equals 5. That's a 3, pretty poor one. R cubed equals 5 on pi, and therefore r equals the cube root of 5 on pi. You can go find out what that is using a calculator. I'm not going to, but it's a real number. And what we have not yet shown, but what we will show, is that actually gives us a minimum value. So just going back a step here, we've got dA on dr equals 4 pi r. I'm going to return this to the form that it was in, minus 20 r to the negative 2. That's before I've made it into a single fraction there. So what I'm going to do now is I'm going to go find the second derivative. Well, why would I use the second derivative? I'm going to use that to show that it is in fact the minimum value here. And I'm going to go and show that d squared a on dr squared, second derivative of a with respect to r, is 4 pi plus 40 r to the negative 3, which is 4 pi plus 40 on r cubed. Okay, one of the restrictions we've got here is straight away is that h and r, considering they're both lengths, h is greater than 0 and r is greater than 0. To be a shape, that must be true. Now, straight away, if I put in any value of r into here that is positive, then this expression here, the second derivative, will be positive. Now, of course, I could put a negative a for r in there. I could put in negative 1, for example, and that would give me 4 pi minus 40. That's clearly going to be negative, but we've just said this must be true. R must be positive, so, well, now I know that my second derivative, if r is greater than 0, then d squared a on dr squared greater than 0, and a minimum exists. Okay, and that's because that means that if I've got my first derivative being 0 and my second derivative being positive, it means I've got a concave up section of the curve, and that's a minimum turning point, which gives me a minimum value for my surface area here. And if we think logically about this, if we made it a really tall and skinny shape, the surface area would be very large. If I made it a very flat flat shape but not very high, think of a pancake, well again the surface area will be very large for those 10 cubic meters. So really we have no maximum area here. There's no dimensions that I can give to make the area a maximum, but there are some dimensions that I can give to make the area a minimum. And it is, as we just found on the previous page there, it was where r equals the cube root of 5 on pi. Now you could simply go and put this value here into the second derivative. Okay, you could go put that into there and confirm that it's positive, but we've just decided that it's going to be positive because 4 pi plus 40 on a positive number has to be positive. So I think that really covers off our 5 marks there. Essentially, the main thing that you should take away from this is, again, that step-by-step approach. Set up those 2 equations, go turn them into a single equation. That's normally step 1 of the question, part 1 of the question as it was here. We're going to be differentiating. We're going to be finding a value that lets that first derivative equal 0. And then as always, you've got to test that is a minimum or a maximum using the second derivative or by using a little table and showing that there is a change in the gradient of the curve. So look, don't be daunted by a MaxMin problem. If you get one in a question 10 or a question 16, it's probably going to be pretty tough anyway, but just do your best and see where you can get some marks.